Okay, greetings aspiring scientists. Thank you for joining me today and welcome to my video on introduction to energy levels and emission spectra and electron configurations. Continuing on from my atomic theory videos from a couple days ago. So let's get right into it and go to my slides. So we're in structure 1.3 now, electron configurations section of the IB chemistry curriculum. So we have another new guiding question. How can we model the energy states of electrons in atoms? So I've introduced in previous videos how the atomic theory, or the theory of what atoms were, evolved and was modified through new evidence. And some of the new evidence was the idea that electrons are not equal to each other in the places that they exist in the atom. They require different amounts of energy to remove different electrons. So we want to try and show how that came about and what we can do with that information today. So by the end of 1.3, it's probably going to take 2 or 3 videos, but we should be able to answer this question. So start with 1.3.1, electron configurations, emission spectra. Alright, so first thing we need to know is what are electromagnetic waves? And again, this will make a lot more sense to you after you've studied waves in physics, if you're in that class, or trigonometric functions in mathematics class. But for now, I'm just going to give you the basic idea of what waves, and specifically electromagnetic waves, are. So, electromagnetic radiation waves are composed of perpendicular, that means at 90 degrees to each other, electric field and magnetic field waves. So there's 2 types, a magnetic field wave and an electric field wave that are at 90 degrees to each other, and they'll both be traveling in some direction, and that direction is the direction of energy transfer of this wave. If you think of it as a photon particle, it's just the direction that that particle is traveling. So some things we need to consider about this. We need to consider its wavelength, which is kind of how long a repeating section is. So it's the distance from one of these peaks to the next peak in the wave. And you can look at the red or the blue, doesn't matter. Their wavelengths should be the same. But we're going to label that with a Greek letter lambda. Okay, and that will usually be measured in length units like meters or nanometers on the small scales that we will be working at. We can also consider the frequency. This will be labeled with Greek letter nu. Okay, it looks like a V, but it's not a V. Luckily on an exam you don't really have to say how it's supposed to be said, you just have to write it, but you should know. This Greek letter on the right is nu, it's a frequency, and we measure it in how many times something happens per second. So the units are seconds power of -1, or you can say per second, per 1 second. So we'd like to know how many wavelengths are generated per second, or you can imagine we just choose a point in space and we say how many wavelengths travel through that in 1 second, per second. And because we're dealing with very small wavelengths, we're going to have very high frequencies. Alright, so these are the important things we need to know for now. If you've already studied waves, you know there's a lot of other things we could consider. We could consider the amplitude, which is how high these peaks get relative to a zero baseline. We could also talk about the time period and many other things, but just wavelength and frequency will be good enough for today's lesson. Oh, sorry, let me go back one. Alright, so what do you know about electromagnetic radiation? You probably know more than you think. Here on my slide here I have representations of most of the categories that we can group electromagnetic radiation types into. So as they get longer, you move towards the left side. As they get shorter, We move towards the right side, speaking in terms of wavelengths, the distance from peak to peak. So on the left, radio waves. These are things like what would be sent to your radio to listen to music or news or whatever. Quite long wavelength. Usually getting around like 1 meter or more. Microwaves are less than, but these are what you would use in your microwave at home to actually cook things. So they can generally be around the size of your microwave, is like that kind of wavelength. A little longer or a little shorter as possible. Then we get into infrared waves. These are quite a bit shorter, but still we are not able to see them with the human eye. We can't see microwaves or radio waves either. But infrared is important because pretty much all objects that have some heat radiate electromagnetic radiation due to their heat, and most of it is in the infrared section of the spectrum here. So that's how like a lot of night vision goggles work. They detect infrared waves, so even though there's no visible light going around, things that are hot release infrared waves. Then right in the middle here, we have visible light waves. This looks like a huge section on this slide, but the range of wavelengths for visible light is actually quite small compared to the range of everything else. It's just a couple hundred nanometers where we can see with our eyes various different types of visible light, and our brain understands them as colors, going from red, orange, yellow, green, blue, indigo, violet, or Roy G. Biv if you learned that acronym in elementary school maybe. But I do want to mention on this slide that this color spectrum is a complete continuous visible spectrum. There's like no gaps or cuts or lines here in the spectrum. It smoothly flows from color to color, and you could almost infinitely zoom in and see different colors and wavelengths. So we're going to contrast that with an incomplete or a discrete spectrum later. So I just want you to understand this one that we're looking at now is a complete continuous spectrum. But beyond violet, you can get shorter wavelengths. We get into ultraviolet. These come from the sun very often, give you sunburns and cancer if you're not careful. They can also disinfect things or cause various chemical reactions to occur. Beyond that, even shorter wavelength, we have X-rays. You might have had these to check your teeth or your bones at the doctor or the dentist. And gamma rays, the shortest. These are mainly due to cosmic activity and nuclear reactions occurring between unstable isotopes, those kind of things. Quite high energy, but low wavelength. Alright, so let's keep that in mind as we move on. So I want to remind you, if you haven't watched my math and science communication video, one of the important things we need to understand when we look at the mathematics, the equations connecting various different properties, is proportionalities. So we've got directly proportional things. If one variable y is directly proportional to x, written with an alpha sign, we're going to get a straight line with some slope that depends on any constants that are in that equation. Another one that might be important today is y proportional to 1 over x, and also 1 over x squared or cubed. Basically all of these relationships in graphs will look very similar. It's like a curved line that approaches both axes as you get to the extremes. So let's keep that in mind, and just remember what happens when we double or half variables in that equation. So for direct proportionality at the top here, if we double x, y must also double. If we half x, y must also half. The opposite is also true. And then inversely proportional, if we double x, y will half. If we half x, y will double. And if we happen to have at the very bottom here, y proportional to 1 over x squared, we'll double x and get 1/4 y, and half x and get 4y. these relationships will probably be important in this video and or the next one that I make, so let's keep that in mind. So let's get into some of the first equations that we'll really look at: energy and wave equations. So wavelength is inversely proportional to frequency, just like on the previous slides I showed. This is an inversely proportional relationship, like y proportional to 1 over x. But instead here we have wavelength proportional to 1 over frequency. And all proportionalities must have some constant. Sometimes that constant is just 1, but in this case it's not 1. It is a very special value. It is c, the speed of light at 3.00 times 10 to the 8 meters per second. That's something else perhaps I should have mentioned on my electromagnetic wave first slide here depicting the actual wave. All electromagnetic waves travel at a certain speed, and that speed is the fastest speed in the universe. It's the speed of light, which we're going to label with a c, and we'll call it the speed of light with 3.00 times 10 to the power of 8 meters per second. That's in your data book, I think, for chemistry, and you can check it anytime. So we have frequency as nu in seconds to the -1, also known as hertz. You might have heard that before. You can use either one for the units of frequency. And sometimes that will be written as an F, especially more in physics, I think. They write it with an F. So that's a very important equation. That means if you know a wave's wavelength, you also know its frequency. They're just connected through this equation and through the proportionality constant c. What about energy then? So scientists did experiments and tried to relate energy or changes in energy to changes in frequency and wavelength. And what they found was when they doubled the frequency of a wave, the energy also doubled. So that's a directly proportional relationship written in the bottom here, bottom right. And then for wavelength, well, if frequency and wavelength are inversely proportional, we must also have that energy and wavelength are inversely proportional, because energy and frequency are directly proportional. These kind of relationships must be true to logically make any sense. So E directly proportional to nu, energy directly proportional to frequency, and energy will be written with special units of joules. And that's not an SI base unit. I think it's kilogram meter squared per second squared in SI base units. But we'll just keep it as joules for now. That's fairly common use. And energy is proportional to 1 over lambda, 1 over the wavelength of that electromagnetic wave. So, proportionality involves the alpha sign, right? But we want to show equivalence. We want to actually know what the proportionality constant k is. So I think scientists did quite a few experiments, maybe drew some graphs with certain slopes as they changed these variables, and they found the slopes and the proportionality constants were a particular number. And we now call that Planck's constant, after the famous scientist Max Planck. It's not Planck. I might say that sometimes by accident, but from what I know, it's actually Planck is the correct pronunciation. So that number ends up being a very, very small number. 6.63 times 10 to the minus 34 joule seconds. Okay, that's not joules per second. It is joule seconds multiplied together at the same time. Just keep that in mind. So we get E equals h nu, or Planck's constant, times frequency. And E equals hc over lambda. Remember that nu equals c over lambda, so we can just substitute that in. So what this means is if we know the wavelength of any wave, we also know its frequency and we also know its energy. Just through a couple transformations using constants, Planck's constant and the speed of light c, we can convert any one of frequency, wavelength, energy into any of the others. Very useful and very commonly on paper 1 and 2 questions in the IB exams. Okay. So we're going to get into the emission spectra and absorption spectra. But first, I'd really like you guys to understand how we get these. Sometimes it's possible to do them in the laboratory of your school. It's not really possible at my school. So I need my students to imagine, and I'll need you to imagine how these different color spectra of visible light are generated. So if you have a hot, high-pressure gas or solid, and you pass the light that comes out of that through a diffraction gradient of some type, for example, like a prism maybe, as shown here on my slide, then the light that reaches your eyes will be a continuous visible spectrum. All the colors there, basically all the wavelengths you can imagine. However, if you sort of release the pressure of that gas, but keep it hot, and then you spread out the light, you won't get a continuous spectrum anymore. You'll get specific lines at specific wavelengths, and the other regions remain dark. So, what's the difference here? Well, hot, low-pressure gas, I think these single lines that we see come directly as a result of electrons transitioning between different levels in the atom. Whereas hot, high-pressure gas or solid, from my understanding, I'm not an expert physicist, but there's going to be a lot of collisions happening between these particles that are hot and high pressure between each other, between the walls of the container. And any time that a charged particle accelerates, and that means increases its speed over time or decreases it, maybe it stops completely. Anytime it accelerates, it releases a photon and some electromagnetic radiation. And because there's a whole range of speeds going on there and different accelerations, basically everything is covered. All wavelengths. So that's what we're going to see. In a lower pressure system, in the second line here, there's a lot less collisions going on. Things are separated out. They're still hot. And electrons within atoms can transfer between different levels in the atom, but particles themselves will not be accelerating as much, either colliding and slowing down or speeding up. And so we don't get the full spectrum anymore. We get the energy level transitions of electrons only instead in the atoms. Then the last case here is kind of special. So this time we have a hot source, and that itself you can just imagine as the first line here. It's a hot, high-pressure gas or solid emitting a continuous spectrum. Okay, so that's what we would see. But instead of that, in between our eye and that hot source and the prism, we have a cold gas, just regular, not hot, regular pressure gas. So on its own, that would not emit any light, but it can absorb light. So what we see instead is, instead of our complete visible spectrum, lines are cut out from that. We get black lines in a continuous spectrum. And you'll notice that those black lines basically perfectly match up with the emitted lines from the second spectrum. And this is a key idea. Whatever this gas, it should be a pure element or compound, whatever it can emit when it's excited is the same as what it can absorb when hot source is nearby it. When the hot source is providing a full spectrum, the cold gas, those atoms will absorb the exact same lines that they could emit when they were excited. Okay, just before we move on, I want to make sure we understand the difference between continuous and discrete in a mathematical or scientific sense. So specifically talking about mathematical functions, continuous on the left here, you can see it's a nice smooth curve. So this is defined for all real numbers in its domain. There's no gaps, no jumps, no breaks in the graph. You could draw that shape without lifting your pencil off the page. And it has infinitely many points between any 2 points. So you could zoom in on this at any location on the line and there'd be no breaks. You can zoom in forever, infinitely, essentially. So those are continuous functions, things like most polynomials, sine and cosine functions, nice continuous functions. On the other hand, discrete functions. These are defined only for specific separate values. They consist of isolated points. There are gaps. The domain is typically integers or a countable set. So things like 1, 2, 3, 4, and not 1.25 or 2.666. Often they'll just be the integers, the regular one-digit numbers. Doesn't have to be, though. If there's any gaps at all, it's still discrete. So it has gaps between these defined points. Okay, so assuming we can understand that, that's going to help us define some things in chemistry here as well. So the spectra that I showed you were of a particular gas, and that gas is hydrogen. And these are the lines that it either emits or absorbs in the visible spectrum. And what do these lines mean? Well, hydrogen cannot emit a full continuous spectra when it's at low pressure. So something about this is discrete. It's only emitting very specific wavelengths, specific lines. Same thing for when it absorbs. It can't absorb all visible light radiation. It only absorbs a few specific lines, 4 in this case, that we can clearly identify. So this leads us to the idea of quantization and photons. So, to clearly define this quantization, the idea that at a quantum scale, extremely small scale, many physical properties are not continuous, but rather they are discrete in small packets called quanta. Okay, so when we think about energy, we can't think about it as a continuous form of something. It is instead discrete. Same thing for energy levels inside the atom. It's not a continuous, system of levels where an electron can be anywhere. It can be in very specific positions. A photon, then. This is the name for a packet of electromagnetic radiation. The energy of a photon can be described as E equals h nu. Energy equals Planck's constant, h times frequency nu. So we already learned that equation a couple slides ago. But now I'm telling you, instead of just calling this the energy of the electromagnetic wave, it's the energy of a packet of radiation called a photon. But this packet of energy and the electromagnetic wave simulation kind of visualization I showed you are essentially the same thing at the same time. It's very hard for our minds to wrap around this, but sometimes photons are imagined as waves, sometimes as packages or particles, and they have properties of both. Alright, so recall energy equals Planck's constant times frequency, or energy equals Planck's constant times speed of light divided by wavelength. Okay, so that's it for 1.3.1. I think we'll stop this video here at 24 minutes, and we'll move on to 1.3.2 in the next one. So thank you very much for listening. I hope you learned something new today. That's all. See you next time.